In this obligatory introduction video, I want to talk a bit about what physics is, which I think is kind of a more interesting question than it sounds, because there's a lot of philosophical debate over the best way to classify it, or how best to sum it up in one sentence, or even what distinguishes it from the broader concept of science in general. And there's a reason for that. Physics is incredibly broad in what it describes. It describes how objects move and interact with each other. It describes falling and rolling. It describes electricity and magnetism. It describes heat and thermodynamics. It describes waves and light. It's the basis for pretty much all forms of engineering. And just about any natural scientific law you can think of is either a physics law or has roots in physics. It's a broad topic. One thing that's less ambiguous, though, is that we can classify it as a natural science, which basically just means that it studies the natural world as we see it and how it works, just like chemistry, biology, or geology. So we can at least distinguish it from the social sciences, which focus on human behavior and culture, like sociology or economics, or from the formal sciences, which are based on logic and rules that we've invented, like mathematics or statistics. A common in-a-nutshell definition that I see a lot is that physics is the study of motion. This isn't a bad definition, since most things in physics do involve some form of motion. There are some exceptions to this, though. There's a whole branch of physics called statics, which is specifically focused on how objects behave when they aren't moving, or when we don't want them to move. One thing that pretty much every area of physics has in common is that there's usually some connection to the concepts of force or energy, both of which we'll talk about in great detail in later videos. There's also often some element of objects interacting with one another, and how these forces and energies can transfer. I think the definition that I would personally give would be probably more along the lines of the general behavior of matter in the universe, and the laws that govern them. Like I said earlier, though, this topic is a bit subjective, so don't take my opinions as fact. Now, physics is commonly known as the fundamental science because of how broad it is. Most concepts in chemistry, for example, are rooted in the principles and discoveries of physics. Many other areas of science are similarly based on physics. Some, like biology, are more based on chemistry, but the root in physics is still there. This can be another subjective issue, though. Some would argue that physics is not quite so fundamental, since mathematics or ontology can be seen as prerequisites. But in the world of natural sciences, physics is still the starting point. If you want to get into physics, there are a few things you want to be aware of beforehand. First off, it is extremely math-based, like very much so. And I'm not just talking about algebra. Most areas of mathematics and their techniques were developed as tools that we could use to solve physics problems. And that's not to say that you need to know everything about every branch of mathematics if you want to get a physics degree, but just be warned that most universities will at least expect you to be well-versed in calculus and differential equations, and that upper-level physics classes might also flirt with some linear algebra, probability and statistics, complex analysis, and others that I've listed here. My point being, if you want to get into physics, be careful if you aren't a big fan of math. It's also worth noting that physics is a very experimental science, so any knowledge that we have on it generally comes from experiments that we've carried out. If your goal is to become a good physicist, you not only have to have skill when it comes to solving problems, but you also want to be good at coming up with and carrying out experiments that can be used to take measurements and interpreting the results of them. Measurements that scientists make can be used to support an idea or a model, but if we find other measurements that seem to contradict those ideas, it doesn't necessarily mean that the original hypotheses were wrong. They may have just been incomplete. A very famous example is Galileo's law of falling objects. In the 16th century, many scientists, including Galileo, argued that all objects fall at the same rate, regardless of how heavy they are. This might seem weird, since it's actually kind of easy to find exceptions to this. A bowling ball will obviously fall way faster than a feather or a leaf, but that doesn't mean that Galileo's ideas were wrong. They're just incomplete if you ignore other factors. A leaf will fall slowly because it's so wide that it catches on the air around it. But if we look at the objects in a vacuum, where we no longer need to worry about air resistance, then we can see that everything falls alongside one another. So Galileo's ideas work, we just need to think about the range of validity that a law has before deciding whether or not it needs to be adjusted. You've got a lot of work ahead of you, but as daunting as physics may seem, it's incredibly rewarding when you take the time to understand it. Good luck!